This is Industrial PLC Applications Level 2, and this video is on Project Requirements, Part 2. With any PLC project, the first thing that you do is conduct a preliminary investigation. Before doing anything, it is important to understand the process. Before any construction, programming, or design is contemplated, understanding the process is absolutely essential. As a resident electrician or technician, being familiar with the process is absolutely job one. As you're conducting this preliminary investigation, you need to ask yourself a lot of questions. What does the facility do or manufacture? How is this accomplished? What equipment is being used? How does it function? How do we maintain a safe operation? Into the existing equipment. Are we tying into it? Is it brand new? What has been provided? What do we need to provide? During the building of a system, some equipment may not have been installed. Is something missing? These deficiencies must be identified with parts sourced and purchased. Then, of course, there's the entire question of spare parts. Does the customer have any parts on hand? Does the customer prefer any manufacturer? When supplying parts, it's economical to order the parts the customer already uses. They're using the same item in multiple occasions reduces the number of stock spare parts. If the same push button is used at 20 locations, only 2 readily available spares may be needed. If different push buttons are used, then at least 2 spares are needed for each different variety. Now that we have that settled, we can start to look at the equipment and its requirements. Does the customer's equipment have special requirements? Is it a hazardous location, adverse environments, additional safety regulations? The equipment must be approved for the location, such that it will not be a safety concern or become damaged quickly. Are they using the equipment or standards of which you are unfamiliar? Are you familiar with OSHA or OSA, MHSA, CSE, OESC, NEC, EU, building codes, accessibility standards, environmental regulations, fire code, hazardous location, and TSSA? All of that has to be established. Now that we have all the equipment established and set aside, we now have to start thinking about connecting the field devices. So an I/O diagram must be provided by either the customer or ourselves. An I/O diagram shows how the external field devices are interfaced with the controller. It's accepted practice to only have one field device for any I/O point. The diagram wirings we're about to show you have the devices and the supply voltage shown. Every PLC installation has a proper informative set of prints. These give you important information and technical requirements. Notice on these drawings that the signal power flows through the input to the PLC. The inputs are shown on the left, just the same way you'll do it when you're programming logic on the PLC. Outputs are generally shown on the right. Again, the same as you'll program on a PLC. The symbol that's shown in the box that looks like a limit switch are proximity switches. With output drawings, notice that the signal source emanates from the PLC output module itself. Basically, the power is fed to an internal common. When an output is true, a set of contacts close and the power goes to the device. Okay, we've gathered all of the fundamental information we require. Now we know what we're working with. We need a description of the requirements so we can begin our control planning. We're going to look now at the requirement analysis form. Let's not forget what we learned last week. Organization is vital. So begin with the description either provided by the customer, your notes, or from a proposal. In our case, it's from Slate. Copy and paste the project description on the blank part of the form. Then, read through the requirements and highlight each requirement with its assigned color. Functional will be yellow, which is supposed to figure out what happens. Properties, which will be orange, What do we need to know? The variables, the timers, the code rules, etc. And then the technical, which will be green, and they will identify program-specific requests or standards and requirements. You can copy each item as you are highlighting it and then rough paste it into the appropriate section. Through this entire process, you should always keep asking questions. There's lots of things to consider and questions you need to have answered. How is safety provided? What should this control do? What are the main objectives? What would go wrong with the operator's use of the control? What could fail in the equipment which would bypass the purpose of the program? As we start our programming, there's some terms we should be familiar with. The first is routine. A routine is a cycle or operation performed by a controller. A latching control for a motor is a routine. An ancillary routine is a routine in a PLC program that supports or enhances one of the primary operations. For example, with our motor starting, it may be the ancillary that looks at the motor overloads. A trigger point is a variable or I/O point that causes a routine to commence. There can be one or many trigger points used to initiate a routine. A start push button, a motor contactor closing. These are trigger points. So looking at trigger points, when selecting trigger points for a routine, select those that give the best indication of the conditions to initiate that routine. More than one is preferable. For example, if the system is to count how many times a motor has run, you must count how many times the contactor has been energized, not how many times the start push button has been pressed. Some of the trigger points that do the best indication will provide feedback, will provide status, and will provide a confirmation of change of. If intended motion is detectable, you should include that. Be aware it may be a part of a combination of trigger points. As you watch the video, you can see distinctive steps in the process. Each of these have a different set of trigger points. When planning the control, look to identify these triggers as the foundation of your program. Let's watch the video again and see if we can determine how many trigger points we see. Cans in position, nozzles lowered, filling started, filling complete, nozzle clear, filling cycle complete, cans are clear to leave. We should also expect the unexpected. Keep in mind that an operator's control panel is an interface between the operator and the machine. You must prevent the operator from making a mistake or anticipate actions that the operator may unintentionally do. The operator may press the start button many times while starting a motor. I mean, how many times have you multi-clicked a control or clicked the wrong control on a computer mouse when using one? We've all done it. Okay, so we have already covered a lot of ground, and there's a lot of things floating around that we're trying to quantify and sort out. So now this is where the rubber starts to meet the road. We're going to go from concept to control. The first thing we're going to do is sort and group. So number one, record all the functions and programming parameters. Use the documents provided. Here's where the RAF really helps you to focus and sort things out. 2. Group the functions into routines and then determine the order of operation. By the way, if you've ever drawn a flowchart, then use it. Anything to help improve your understanding of the project is great. Okay, we've covered a lot of ground again, so now it's time to get busy and get started programming. So number 3 is there is no hard and fast rule, but it's better to start creating small programs by the functionality required of each routine. Name them something that's easy to remember, but is also purpose-driven. Avoid ambiguous names like Step 1. Well, what's Step 1? What's that? You can start by creating a series of empty programs which will represent each routine required, even if you are certain the program will only be 1 or 2 lines of logic. Don't worry, you can always delete them later if it's too much. The next phase is to write, build, and test. You can see on this particular project, the programmer has divided his entire project into 5 routines. If it's time to write the logic, then the 4th thing you think of is to start the routine that you are most familiar with and write the logic. Keep it short and simple. If doing a stop-start on a motor is your most favorite easy one to do, then start with that. Number 5, build and test that routine. Verify that your building block program works. You would be surprised how often the same old, simple, trusted logic failed because the programmer hurried and didn't check if the I/O addresses were correct. By breaking up large projects into smaller routines, you really help logic digestion. You're not programming for yourself, but for your employer or your customer. You may not be the person called upon to troubleshoot the program later. By making each routine a specific function, it's easier to digest what the logic does and how it fits into the whole process. Notice in the example, the 5 routines are clearly labeled by their function. So 6 months later, long after you've forgotten all the logic you wrote, you may get a call saying the machine doesn't work in manual. Well, I'm guessing you'll go to the routine called manual operation to start your troubleshooting. And then it may only be a quick refresher on the few rungs of logic to determine the problem. We're just about done here. We've gone from concept to control, and now we're going to go from control to flow and go. The second to last step is to make sure the routines are in logical order, just as the way the processor is going to execute the logic. The last step should have been done along the way, but just in case there might have been some changes or something or other, make sure you have every rung commented and a header rung for each program. And put your name on it. Take some pride in your work. Now, we're going to take a look at some common sense practices from the pros. All right, here is pro note number 1. Safety first. Place all safety instructions as near to the left rail in the rung as possible. Ensure that instructions pertaining to safety are clearly identified with commenting. If a safety device has stopped the process, you don't want to scan through several branches or nests to find it. It should be right out in front. If you look at the logic below, that's exactly what they've done. They have all of their safeties on one rung saying e-stop circuit. That in turn sets out an output called safety ready, and the safety ready is going to be ahead of any other rung of logic to execute. Pro note number 2, last order wins. You may have several routines attempting to control a single variable, like a bakery changing the temperature to the same oven when it does muffins as opposed to cookies or bread. In this case, you will need to create some global surrogates. Notice that 3 different bits can turn on digital output 0, 1. Each bit is controlled in a different routine. Once the routines have sorted out the actual control, the last program in the flow does the actual turning on of the output. Remember, your I/O number may be set, but the number of internal variables is only limited by the PLC's memory, and that's thousands. Here's pro note number 3, the power of nothing. While doing your testing phase, use the NOP instruction as a placeholder. It doesn't change the logic, but gives you a place to put other instructions. Keep in mind, it will not work for all situations, but when you're doing your testing and building, it's a great practice. Put ahead a contact that you may need, and once you're done, it's a simple matter of removing them if you don't require them. By now, you should be well on the way of completing your first lab. Remember, you should have the RAF approved and then do the logic. And do not forget to do the online quiz as well. See you in class.